So this is interesting. So should we have our practice exam the weekend, like at the end of this weekend, or the weekend at the end of Thanksgiving break?
I'd say end of break.
Like so after the break?
Yeah.
Okay.
Like
All
the
right.
like right before the week of the exam.
Yeah, because then it'll be fresh in your mind.
Right.
Um, okay. Oh wait, let's vote. So trying to make it unanimous. So I think it's always best to do the
What about on a weekday?
a weekday for the practice exam.
Well,
That's a good question. I mean, I think the reason why typically it has gone like a little over an hour is because there are questions. So I'm kind of worried if we have it during the week that we won't be able to finish it in 1 hour. Um, yeah. Okay, so let me see the hands of who does not want it on the weekend after Thanksgiving. Anyone does not want it on a weekend after Thanksgiving? Okay. Then, since no objections, we'll have it that day. Now send an email out to everybody else. Okay. So, yeah, then we just have this right here. Oh, and since we moved the exam from here to here, yeah, I'm gonna come up with something for this day. Maybe it could be a review for the final or something. I don't know.
That's a good idea.
Okay. So, oh, let me get. Okay, so for review, so remember last time we were looking at the frequency response, and what we did, we said, well, typically these systems, these amplifiers will have some kind of frequency response that looks sort of like this. There'll be some variations, but typically there's a mid-band region that we can call, and from that mid-band region, that's the most interesting part because we're typically concerned about this region and anything outside of that, right? So we're typically concerned about the amplitude of this midband and also where the low and the high frequency cutoffs are. If this was just a low pass, then this piece right here would go all the way to 0. If this was a high pass, then this right here would just keep going up very high. And so what we did, we said, well, what we can do for our analysis to make it easier for us to look at, we'll take the gain, and this is AV, the magnitude of AV, the output over input of your amplifier, and we'll break it up into 3 factors, okay? We'll have this piece right here, this A mid, which is the amplitude of this right here. Then we'll also have this component, and this component right here concerns what happens in the low frequencies. And in the high frequencies, this FL component becomes 1, right? So it does this and then becomes 1 all throughout. And then we multiply it by this FH, and this concerns the high frequencies over here. And at low frequencies, this becomes 1. So it does this part correctly, and then once it gets over here, it becomes 1. But when you multiply all these together, all 3 of these, it becomes this right there. And so we looked at, we broke this up into 2 pieces. We looked at the gain, AL for low frequency stuff. That's the mid band plus FL. And we looked at the high frequency part. That's the A mid plus FH. And then from that, we looked at the poles and the zeros. So from FL and FH, we're able to get the zeros. We're able to get the poles from those. And we're able to exactly find where the low frequency and the high frequency were very accurately. And we did that by remember we had set these values right here to, well, so this piece alone, it maxed out to 1, right? And for the cutoff, we were concerned about 3 decibels down. So we made that equal to the magnitude of 1 over square root of 2, which is negative 3 decibels. And then we solved that to find out what frequency did that occur, and then that was this frequency. We did the same thing with FH. We set that to 1 over square root of 2, which was a cutoff, which is like right there. And then we solved for the frequency that made that true, and that was that. But this right here is for any number of poles and zeros, any number of poles and zeros. Okay, so that's what we did there. And so for this lecture, we're going to take it a step further and answer the question, you know, what if you don't know where all the zeros and poles are? How can you find the most important thing you're worried about, and that is the cutoff frequencies of that? And so that's what this lecture is about, is estimating those kinds of things if you don't know the exact equation. Okay. Okay, so continuing on with where we left off last time, we were looking at this where we had taken this common source, and it was common source because if we put this in the high frequency AC domain, then what happens is that this becomes an AC bypass, and so the source right here gets grounded, and it becomes a common reference point for both input and output over here. So it's labeled a common source, and when we looked at it in terms of low frequency, for low frequency we can't get rid of the capacitors because their impedance values at low frequency, so those remain. However, we could do a few things. So for example, actually, yeah, okay, yeah, this model right here is actually, there was another model of this that was 1 level up, and then this model right here became the low frequency DC, the low frequency model, because we had this other component right here that went to the VCC at the top, and then that became grounded. Okay, so that's where we have this. That's why this is grounded, because of that. And then we had taken this, and then we had converted it to a small signal model where we're able to linearize about the Q point, and the slope of that linearization is 1 over this transconductance value. And that's where that is from. And then from there, we did our analysis. So basically what we're trying to do is find out what the output over input was from this circuit for the CS circuit. And then we're going to determine what is the high and low frequencies from that. Basically this and this right here. Okay. So what we did, we needed output and input. So we started looking at what's happening over here. And so we have this as the current I0 going across this R3. And you can see it's in terms of VGS, you have the transconductance, and you have this. And that was done by current division that we went over last time. And then we plugged it into here. And then we got the voltage across R3. And that's how we got this expression right here. So we just had taken this, plugged it into here, and then we got this. And we need to find out what this VGS is, right? That's what this is. And so that's going to be the voltage at VG minus the voltage at VS. That's VG and VS right there. And the voltage at VG is found by voltage division. Unfortunately, it's in terms of VI. That's actually something we want to figure out what the gain is, which is output over input. So that's going to be over that input right there. So we did that by voltage division, and we did this by KCL to find out what Vs is. And we had taken those values. We had taken this and this. Wait, so we had taken this, plugged it into there. We had taken this, plugged it into here and here. And then, if you guys can see that, then this expression right here would be all in terms of some stuff with this VI that we could factor out of that. Because this term is going to have VI in it. And when we plug this into here, this over there is going to have VI in it. And then we take that, plug it into there. So this whole thing is going to have some stuff with VI. And then we have the ratio of V out over VI. Okay? So anyway, so this is what GS is right here after cleaning it up a little bit. And so what the gain is, which is V out over V in, it looks like this. And since we're dealing with the low frequency regime, we put it in terms of this, where we're going to say, well, it's going to have two factors. It's going to have the A mid factor. It's going to have the FL factor. And then we identify what those are. So here's the A mid factor right here. Okay, and that's just, some constant. It's not a function of frequency, as you can see. And here's FL, and that is a function of frequency, S, and that's right here. And remember what S is. That's complex frequency, right? So S was that sigma plus J omega. So that is the variable we're concerned about on our Bode plot. So that's what this is right here, and that's what FL is. And then from there, once we know that, then we can start looking at our poles and zeros. So here's that expression. So one interesting thing to note is that there are, just looking at that, there are going to be 3 poles and 3 zeros. And you can see that because there's a pole and zero for each independent capacitor. So we have capacitor 1, 2, and 3 right here. So that right there, they're all independent capacitors. That will tell you how many poles and zeros you're going to have from this analysis. And there are 2 of the zeros. They occur at S equals 0. You can see that right there. Okay, so it's a double 0 right there, second order 0. And those correspond to series capacitors of C1 and C2. Both of those block the signal, the DC signal. And here's the circuit right here. So we're talking about C1 right here. That's blocking that. Here C2 is blocking that for the output. Okay, so that's going to be a 0. Now the third 0 occurs at a frequency for which the impedance of the parallel combination of RS and C3 become infinite. So that's this right here. So when this whole block right here, when that impedance becomes infinite, then it's blocked, right? And you get a 0 from that too. Okay, so those happen right here. You get a double second order 0 right there. Another one happens when this term right here becomes 0. And that's this one right there. When that RS and R3 right here, when this impedance becomes infinite to block the signal going through in the frequency domain. And that happens at S equal negative 1 over RS C3 right there. Okay, so now for the poles, that's the case where each of these factors becomes 0, right? So, and that's easy by inspection. So S just has to be the negative of this term. This S has to be the negative of this term, which is right here. And then this S has to be the negative of this term, which is right here. Okay. So, anyway, that's how you analyze the poles and the zeros for the typical case. So now what we're going to do is try to estimate that. So this is like a different method for looking at those, getting these values for this like omega L and also for omega H. Okay, so it says here, to use a prior analysis, we needed to know the locations of the poles and zeros. But in most cases, it's not easy to find the complete transfer function or even represent it in factored form. We were able to do it because it was like a very simple circuit. Well, kind of simple, but they can get much more complex. However, most often we're just interested in the bandwidth, and that's from here to here, the bandwidth. And so we just need a mid for that, and the upper frequency right here, and the lower frequency for cutoff right there. Right? So we just need this, this, and this, because we're mostly interested in the bandwidth. And fortunately, the knowledge of the exact position of all poles and zeros is not necessary for that. So we don't need to know all of these things, for that. And we don't need to know what's happening here. We're just concerned with this piece right there. And so there's two techniques. And for this lecture, we're going to cover this one right here. And these two techniques are, they produce good estimates of finding omega L and omega H without having to find the complete transfer function. But it does require you to know what the circuit looks like. Or at least estimate what the circuit looks like. Okay, so we're going to use this expression right here. So the lower cutoff frequency for a network having in-coupling and bypass capacitors can be estimated from this right here. So omega L is approximately equal to the sum of 1 over RIS times CI. Okay, and we'll go through many examples of how to get the RISs in the CIs. Okay, now this RIS, it represents the resistance at the terminals of the ith capacitor. So in the last example, we had 3 capacitors. Okay, so I would be 3, and then what we're going to do is we're going to replace the ith capacitor with this RIS. Okay, now the product, this RISCI, it represents a short circuit time constant associated with that capacitor. And so what we'll do is we'll replace, so whatever value of I we're on, we'll replace it with this resistor and try to find out what the effective resistance is. And all the other capacitors, like where I is not equal to the one we're on, we'll just short those out, okay, in order to find the complete resistance. Okay, so let's start with this one right here. So we'll apply this SCTC method to the common emitter, and we'll apply it to all the other ones too. Okay, so why is this a common emitter? Can someone tell me that? Yeah, if we made this a like an AC model, right? Then this would be a bypass capacitor, so this would short the emitter to ground, right? So you just have to try to imagine that, okay? And also that would be ground there too, and other things, but that right there would not be common because you have this RC, but that right there would be a ground. Okay, so here's what we'll do. So first we'll take this circuit, which is a common emitter, and then we'll convert it to this over here. And this right here is this low frequency model. So you still have your capacitors there, so they're no longer not negligible. Okay, so they're not negligible, but this right here does get grounded. So that's why this value right here for going through RC, it goes to ground right here. And now from this, we'll apply our method. So first we'll look for RIS equals R1S. Okay? And so the 1 stands for the ith capacitor. And so the ith capacitor, that's C1. So we're talking about this capacitor right here. Okay? So for C1, R1S is found by replacing C2 and C3 by short circuits. So here's C2. That gets replaced with a short circuit. It's supposed to be right there. And here's C3. And so that C3 becomes a short circuit. And so this R4 is no longer there because it's become shorted. Okay? So here's where C1 was. And now we're going to look at the resistance seen between these two terminals right here. And so if you did that, you would find out that this R1S, it equals this R1 in series with RB and RIB in parallel. Okay, so here's RI. I think I called it R1, but okay. So here's RI, and that's going to be in series with this RB and this RIB. So everything seen in this direction from here is like, just so just think it's like a resistor right here of RIB, and they're in parallel right there. Okay. Another way to think of this RIB is just R pi, as seen like that from that point. If we use a small signal model. Okay. So that's what R1S is. Okay. And remember what this equation is. We have to figure out what all these are, and then once we sum them all together, they equal the frequency, which is really nice. That cutoff frequency. So here's the first one, R1S. So the second one, right here, we did the same thing, but here C2, so we replace C2 with this R2S, and the other capacitors, they become shorted. So this becomes shorted, and this becomes shorted right here. Okay, and then we just find out what is the resistance seen between these terminals, right? So you're going to have this R3, and that's going to be in series with this RC and this right here in parallel, right? This RIC. So you're going to get this expression right here. And that RIC, you can approximate that as R0. Okay? So here's the output of your small signal model. And if your R0 is typically high, right, then you could just approximate that, this whole thing right here, as just RC. Right there. If R0 is much higher than RC. Okay, so for R3, we have to look at the third capacitor, where I is 3. So this right here, now this becomes R3S, and the resistance seen through these two terminals right here is this R4 in parallel with RIE. And RIE is a resistor right here that represents all this. Okay, and this RIE, it can be approximated as R pi plus R thev over beta 0 plus 1. And this R thev is these two guys right here in parallel. Okay. All right, so once we have all these, R1S, R2S, R3S, so now we just plug that into our handy dandy formula right here, and then we're able to back out what omega L is. So this is an angular frequency. If you want to put it in terms of just frequency, 1 over seconds, you got to divide that. You got to divide out the radians. So you divide it by 2 pi radians. Okay. So now let's apply that to a common source. Okay. And So here you can see that the here's the source right here, and it would be grounded if this was a bypass capacitor. So that makes it common with the output and input. And from this, we could apply the same thing as last time. We have 3 capacitors, C1, C2, and C3. So for C1, that becomes our R1S, and then the C3 and C2, those become shorts. So short here, short there, and this is the circuit we get for R equals I. For for I equals 1. For I equals 2, we'll get this. And so that C2, that capacitor, is replaced with R2S. These two become shorted. So that's shorted, and this is shorted right here. And then for I equals 3, this right here becomes the resistor we're looking at. And these other two, that's shorted. And this right here is shorted. And wait, where's the other one? Oh, I'm sorry. This is our resistor, but this becomes shorted, which is right here, and this becomes shorted right there. Yeah. Okay. So these are our 3 circuits right there, and then for our R's from each one of those, we get these expressions right here, and then we sum them all up like this to get our frequency for that one. That's for the common source. For the common base, if we put that in the low frequency domain, then these right here become grounded, and that's why all that's grounded right there. And then from that, we only have 2 capacitors, C1 and C2, so that C1 becomes like this, and that site's shorted, and that C2 becomes that, and then the C1 over here is shorted. And so the equations we get are this right here and this right here. And in fact, you may be able to see that just by looking at this circuit right here, right? So you may not have to draw this circuit every time. If you could just imagine that, turn this into a resistor for R1S and turn that into a short circuit, shorted element, you'll see that this Ri is in parallel with this, this Ri is in series with this Re in parallel with whatever is coming out after that, which is Rie right here. Okay, and same with this R2S. Okay, so for a common gate, okay, you take your C1 and replace it with this, and you short your C2. You take this, replace it with your R2S, and then you short that, and you get these expressions, which is very similar to what we've seen last time. And you get this for your frequency. And for your collector, you want to take this, and this becomes grounded. So that gets grounded right to there. These other 2 remain. So you take this, you have 2 capacitors, you convert this to this, where here's your R1S, and on this one, here's your R2S, and that becomes shorted there. And so here's what you get for your R1S, here's what you get for your R2S. Plugging those in here, you get your frequency for that. And for the last one, for the drain, this right here, your R1S is right here, and that gets shorted. So you just have this Ri in series with Rg in parallel with what's seen here, any resistance crossing this line to the right. And for your R2S, here's your resistance, that gets shorted. So you have your R3 in series with your RS in parallel with what's seen in this direction across that line. That's what you get from that. Okay. So any questions about any of these guys right here? Common collector, common emitter, common source. Okay, that's good. Okay, so now let's look at high frequencies. Okay, so we now explore the upper limits of amplifier frequency response, the high frequency limitations. Now, all electronic devices have capacitances between their various terminals. So basically what they're trying to say is that even if you don't have an explicit capacitor there, right, there's going to be some kind of capacitance just by the nature of the structure itself. Okay, and these capacitances limit the range of frequencies for which the devices can provide useful voltage, current, or power gain. So we'll now develop a description of the frequency-dependent hybrid pi model for the bipolar transistor, as well as a similar model for the field effect transistor. But we'll just do this one right here for now. Okay, so here's the hybrid pi model, but it's the frequency version of it for the BJT. So it looks like this. So compared to the hybrid pi model we are used to seeing, we don't have the capacitors there, right? But now we're going to place the capacitors there because now we're at high frequencies, and before they were insignificant, but now they become very significant, and so we have to include them in the analysis. So there's this capacitor right here. This is like a shunt capacitor. This is this C pi. And we also have this capacitor right here, the C mu. Okay. Now the C mu connected between the base and collector terminals, right here and here, that represents the capacitance of the reverse bias collector base junction of the bipolar transistor. And the book asks you to remember something from chapter 3, right here. Okay. So this C mu is related to the Q point through this equation right here. So here's C mu. And so I suppose this equation came from chapter 3, where it was derived, because it's not derived in chapter 17. It's just given to you. So this C mu 0 right here represents the total collector base junction capacitance at zero bias, and VJC is the built-in potential. And this value right here is typically between 0.6 to 1 volt. That's what that is. And the internal capacitance between the base and emitter terminals here and here is denoted by C pi. That represents the diffusion capacitance associated with the forward bias base emitter junction of the transistor. So C pi is related to the Q point, and that was discussed back in chapter 5. Okay, and that's given as this right here. So you have the transconductance and this value, this tau f. And tau f is, if you recall, it's the forward transit time of the bipolar transistor. And the impedance of this C pi causes the base emitter voltage VBE to be reduced as frequency increases. And you can clearly see here that you have this impedance right here, and as frequency increases, then that's going to change this impedance, and that's the only thing between the base and the emitter. Okay, so as impedance of the impedance of the C pi causes the base emitter voltage to reduce as frequency increases, thereby reducing the current in the controlled source at the amplifier of the transistor. Okay. So here are the things right here. So the shunt capacitance, such as the C pi, those are always present. Okay. These things are always present. They appear when you have high frequencies. If you have low frequencies, you can ignore them. All right. At low frequencies, the impedance of these capacitors is usually very large, and so has a negligible effect relative to the resistance R pi. and that's why you can ignore them. As frequency increases, the impedance of the C pi becomes smaller and smaller, and the VBE eventually approaches 0. At very high frequencies, C mu right here shorts the base and collector terminals together. Okay, so, and these are the reasons why these transistors, they cannot provide amplification at some arbitrary high frequencies. So you have to really understand their limits, low and high frequencies. Okay, so if there's no more questions, then that'll be it for today. I'll see you guys on Wednesday.